Well, students, we have learned different ways to construct quadrature formulas that can be used to approximate the value of an integral for a given function over an interval AB. In this lecture, we will learn how to develop numerical methods for approximating derivatives of a continuously differentiable function. The most simple way to obtain a numerical method to approximate the derivative of a function f of x is to directly use the definition of the derivative that we have learned in our calculus course. This is particularly handy to get a numerical method for first order derivatives. If you recall from our calculus course, f dash of x may be defined as limit h tends to 0 f of x plus h minus f of x divided by h. There are also other ways to define the derivatives. This is one of the ways. The approximate formula can therefore be taken as, just discard this limit and just assume that this expression is the approximate value for your derivative for a sufficiently small h. Of course, this will give you more accurate result if your h is smaller, right? So let us denote this formula by dh plus f of x. Note that you will be given a x and a h. Once these two parameters are given to us, then we consider f of x plus h minus f of x divided by h as the formula to approximate f dash of x, right? So that is why we have h and x in our notation, and this plus denotes that we are considering this particular formula, and it is called the forward difference formula for approximating f dash of x. Now the question is, what is the error involved in using d plus h instead of f dash, right? So in other words, we are interested in deriving a formula for the mathematical error involved in the forward difference formula, and that is given by minus h by 2 f double dash of eta, where eta is some number lying between x and x plus h. Why x and x plus h? If you recall, because the forward difference formula involves the function values at x and x plus h. That is why we have the unknown eta lying between x and x plus h. The proof is quite simple. It is a direct application of the Taylor's theorem. If you recall, we can write f of x plus h as f of x plus h into f dash of x plus the remainder term, right? Now you can see that f of x plus h minus f of x is equal to h into f dash of x plus h square by 2 f double dash of theta, right? Now divide both sides by h, you will get that the forward difference formula d plus h f of x, which is given by this, is equal to f dash of x plus this. Therefore, f dash of x minus the forward difference formula can be written as minus h by 2 into f double dash of eta. So that is how we get this formula, and that completes the proof of this theorem. Let us now see what is meant by the order of the forward difference formula. If you recall, the mathematical error in the forward difference formula is given by minus h by 2 into f double dash of eta. For a fixed x, you can also view the mathematical error as a function of h. Let us denote this function by g of x. Therefore, g of x is actually given by minus h by 2 into f double dash of eta, right? Take modulus on both sides and divide both sides by h. You get mod g h divided by h is equal to 1 by 2 into f double dash of eta. If you assume that f is twice continuously differentiable, then f double dash is a continuous function on the closed and bounded interval AB. Therefore, it will be bounded. Let m be the upper bound of the function modulus of f double dash of x for all x in the interval AB. Then you can see that mod gh divided by h is less than or equal to a constant, right? If you go back to our first chapter on mathematical preliminaries and recall what is meant by big O of a function, that is g is equal to big O of some function, say capital F, for instance. When will you say this? If g of h by f of h is less than or equal to some constant, provided f of h is not equal to 0 for all h, right? Now you can see that the same kind of inequality is established between g and just f of h is equal to h. Therefore, we can say that g is of big O of h as h tends to 0. You should not forget to indicate as what tends to what whenever you use the notation big O or small o. In this case, we will also say that that formula, in this case it is the forward difference formula, is of order 1. Okay. In general, if you find that the mathematical error is of order, say h to the power of some alpha, then we will say that that formula is of order alpha. Okay, here it is 1. Therefore, we say that the forward difference formula is of order 1, or order of accuracy is 1. Let us take an example. Let f of x equal to sin x. Therefore, f dash of x is cos x. Let us use the forward difference formula to approximate the derivative of the function sin x at some given point. According to the forward difference formula, we have sin x plus h minus sin x divided by h as the approximation to the derivative of the sine function. To be more precise, let us take x equal to 0.5. Then f dash of 0.5 is approximately 0.877582. Let us also take h is equal to 0.5, which is pretty large. Then the forward difference formula gives sine 1 minus sine 0.5 divided by 0.5. That is given by this value. I have taken the argument of sine in radians, and that comes to be 0.724 roughly. And up to 10-digit rounding, you can see that the relative error, remember I'm talking not about the mathematical error, which is nothing but the absolute error, but I'm talking about the absolute relative error, is true value minus the approximate value divided by true value, and that is coming to be 0.17 roughly. It means you have around 17% error. That should not be bad because you have taken h to be pretty large. Okay, these formulas will be more and more exact when you go to take h more and more smaller. Therefore, we should not feel bad that we got 17% error in this approximation. Probably if we would have taken h equal to 0.05, we would have got obviously a better approximation. Let's go on with another numerical differentiation formula, which is called backward difference formula. The idea is again very similar. You consider another form of the definition of f dash of x from our calculus course, which is given by limit h tends to 0, f of x minus f of x minus h divided by h. Now again, discard this limit and take the expression alone and consider that as the approximation to the derivative of the function f. For this formula, let us use the notation dh minus f of x. Again, minus is because we are using the function value at x minus h, unlike in the case of forward difference formula where we have used the function value at at x plus h, right? And this formula is called the backward difference formula for the derivative of the function f at the point x. And just like forward difference formula, if you take smaller and smaller value of h, you tend to get more and more better approximation for the derivative of your function. Now I leave it to you to derive the mathematical error formula, or rather the expression for the backward difference formula. And let us pass on to another difference formula called central difference formula. Again, we will use another form of the definition of f dash from calculus, which is given by limit h tends to 0, f of x plus h minus f of x minus h divided by 2h. Again, remove the limit part and take the expression alone and consider that as the approximation to the derivative of your function f at the point x. We use the notation dh0 f of x for this formula, and it is called the central difference formula. Again, as you go on taking smaller and smaller value of h, you tend to get more and more better approximation for the derivative. In all this, we should keep in mind that the h that we take is a positive number. Let us try to derive the mathematical error expression for the central difference formula. In this case, we have to assume that f is thrice continuously differentiable on the interval AB. Then the expression for the mathematical error involved in the central difference formula is given by minus h square by 6 into f triple dash of eta, where eta lies between the points x minus h and x plus h. How to prove this? Well, again, it is a simple application of the Taylor's theorem. We can write f of x plus h as f of x plus h into f dash of x plus h square by 2 into f double dash of x plus the remainder term, right? At the same time, we can also write f of x minus h as f of x minus hf dash of x plus h square by 2 into f double dash of x minus h cube by 3 into f double dash of eta. Remember, the eta in the first expansion and the eta in the second expansion, they are different. Therefore, we will give different notations to them. Eta 1 actually lies in the interval x to x plus h, and eta 2 lies between x minus h and x, right? So that is what is written here. Let us substitute these two expressions in the central difference formula. Recall that the central difference formula is given by f of x plus h minus f of x minus h divided by 2h, right? Therefore, we will also divide the right-hand side of the expression by 2h, and thereby we get the right-hand side as f dash of x plus h square by 6 into f triple dash of eta 1 plus f triple dash of eta 2 divided by 2, right? Well, we can stop at this level, but one can also rewrite this expression in a rather compact way. For that, we can use the fact that f triple dash is a continuous function and then use the intermediate value theorem. If you recall, we have proved a result from which we can get this as a particular case where eta is a point lying between x minus h and x plus h. So you just substitute this expression for the expression in the bracket. Remember, there was a divided by 2 here. If you recall, this is what we have in the bracket. And that can be now replaced by f triple dash of eta. And that is precisely what we want to show as the expression for the mathematical error involved in the central difference formula. You can see this. Also, you can see that the mathematical error is of order 2 in the case of central difference formula, unlike in the case of forward and backward difference formula where we had the order as 1. Let us see the geometrical interpretation of these three primitive difference formulas, namely the forward difference, backward difference, and the central difference formulas. Let this solid black line be the graph of the function f of x. And now we want to find the slope of this tangent line at the point x, that is what is given as f dash, as we all know. In the backward difference formula, what we are doing is, instead of taking the slope of this tangent line, we are taking the slope of this line. That is what is the backward difference formula. In the case of forward difference formula, we are taking the slope of this line, that is the line joining the points x comma f of x and x plus h comma f of x plus h, right? And similarly, the central difference formula is taking the slope of this line, which is the line joining the points x minus h comma f of x minus h and x plus h comma f of x plus h. So that's a very simple geometrical interpretation of these three difference formulas. So we have seen how to derive some simple difference formulas for the derivative of a function. Now, if you recall, these formulas were depending on the function value at two node points. Now, the question is, suppose I want to have a formula for f dash that depends on the function values at more than 2 points. Can I derive such formulas? That is my first question. And the second question is, why only f dash? We also need difference formulas for higher derivatives of f. If you recall, we derived these formulas directly from the definition of f dash that we learned in the calculus course. Now, if you want to approximate higher order derivatives, then it's not that easy to every time go for the basic definition. Rather, the idea is to look for an approximation of your function f by some other function which is more simple or easy to differentiate, right? Once we pose this question, we now know what is the idea behind deriving such methods by approximating our function f by a simpler function. Given that we are familiar now with polynomial interpolations, what we can do is, instead of working with the function f of x, we can work with its polynomial interpolation of degree n evaluated at some node points x0, x1, and so on up to xn, and then simply take the derivative of that polynomial and consider that as an approximation to the derivative of the function f. So that is the idea through which we can generate many numerical differentiation formulas or the finite difference formulas. These are called finite difference formulas. And the method of generating finite difference formulas using interpolation should not be very difficult for us, because we have done such exercises in the numerical integration section itself. Let us just illustrate this idea with some particular cases. Let us take n is equal to 1, in which case we need two node points x0 and x1, and the interpolating polynomial may be written in the form f of x plus the first order divided difference of f at x0 and x1 times x minus x0. Recall, I'm just writing the polynomial p1 of x in the Newton's form. Now just take the derivative of p1 of x, and that gives you simply the divided difference of f at the nodes x0 and x1. And if you agree that you will take p1 dash of x as the approximation to the derivative of f at the point x, then you can see that this divided difference is simply the approximation of f dash of x, right? Now, different choices of x0 and x1 leads to different formulas. For instance, if you take x0 is equal to x and x1 equal to x plus h, what we get is, if you recall, this is nothing but f of x1 minus f of x0 divided by x1 minus x0, right? Now, if I take x1 is equal to x plus h, then that will happen to be f of x plus h minus, if I take x0 as x, then it is f of x divided by, now x1 minus x0 will be simply h. And that is nothing but our forward difference formula. Similarly, if you take x0 equal to x minus h and x1 equal to x, then that leads to the backward difference formula. And finally, if you take x0 equal to x minus h and x1 equal to x plus h, then that will lead to the central difference formula. So the three formulas that we have obtained directly from the definition that we learned in calculus, you see that the same formulas can also be obtained through the linear polynomial interpolation of the function f. Similarly, you can also approximate f of x by p2 of x at some points x0, x1, and x2. With this idea, you can also generate many more formulas for the first derivative of f. And why only 2? You can take 3, n equal to 3, n equal to 4, and so on. And different choices of the nodes leads to different finite difference methods. So once you understand this technique, then you can also establish the mathematical error involved in such formulas. And this mathematical error expression can be directly obtained from the mathematical error expression for the polynomials, right? Let us state this idea in the form of a theorem. Assume that f is a Cn plus 1 function defined on the interval AB, and we are given n plus 1 nodes in the interval A to B. With that, we can approximate f by Pn of x, right? And thereby, you can approximate the derivative of f by simply differentiating that polynomial, right? Then the mathematical error involved in that formula, that is Pn dash of x at any of these node points in particular, can be written by this expression, where this xi is an unknown lying in the interval AB, right? So let's not go into the proof of this theorem. It's not something new to us, but still we will omit this for our course, and we will pass on to an example where we will take 3 nodes, x0, x1, and x2, and thereby we can generate a quadratic polynomial interpolating the function f. Let us write this polynomial in the Newton's form, and it is given by this expression. You can easily check this. Once you have this polynomial, you can use this polynomial to approximate f dash and also f double dash, if you observe. But don't try to approximate f triple dash with this polynomial. You may not get anything interesting out of that. So if you are using a quadratic polynomial interpolation, you can at most approximate f double dash. Let us go on and try to approximate f dash from p2 of x. The expression for this formula is given by this, which is very clear. You just differentiate p2 with respect to x once, and you get this formula for f dash of x. And similarly, you can also get a finite difference formula for f double dash of x. What you do is simply differentiate p2 twice, in which case you will get the formula as 2 times the divided difference of f of order 2 at the node points x0, x1, and x2, right? This is not very difficult to understand. Now let us take different values of x0, x1 and x2 and see how these formulas look like. Let us fix equally spaced nodes for the sake of simplicity with the step size as h. If you recall, the first order divided difference is given by f of x1 minus f of x0 divided by h, and the second order divided difference is by definition f of x1 comma x2 minus f of x0 comma x1 divided by x2 minus x0, right? Now you substitute the expression for this separately and this separately, and then simplify. You will get this expression for the second order divided difference at the points x0, x1 and x2. Therefore, the formula for f dash, which we generated through P2, now can be written as this expression. What I'm doing is, instead of the first order divided difference, I put this expression here. And instead of the second order divided difference, I just put this expression here. That's all. Now, this is the expression that we got for f dash through differentiating P2 of x. Now, in particular, let us take x0 as x minus h, x1 as x, and x2 as x plus h. For any x given in the interval a to b, simply substitute these values into this expression and let us see what happens. As per this, the divided difference formula for f dash of x is given by this expression, and that can be simplified to this, right? These are simple algebra you can do and get these formulas. Why only this choice? We can now go for many choices of x0, x1 and x2, and each one will give rise to a finite difference formula for f dash. Since the nodes are chosen in this symmetric way, this formula is called the central difference formula. Now let us use the nodes x0 equal to x. That is the point where we want to find the derivative of the function f. For that, you use x0 as x, x1 as x plus h, and x2 as x plus 2h. Now, such formulas are called forward difference formula. Simply substitute x0, x1, and x2 in this expression and just simplify it. You get this formula. And as I told, this formula is called the forward difference formula. And one can write the mathematical error for these formulas also. How will you do that? Wherever there is a scope, you expand that with the Taylor formula. For instance, you can expand this in Taylor formula. You can also expand this in Taylor formula. Well, you no need to expand this in Taylor formula. So you take these two, expand in Taylor formulas, substitute those expressions into it. Certain terms will get cancelled and you will finally have the remainder term coming out to be like this. We will do this exercise in one of these formulas so that the idea is more clear. Of course, we have done it for forward difference and central difference for two nodes. We will also do the same exercise for some other case to illustrate how to get the mathematical error for any such finite difference formulas.